Today's lecture is going to cover both the translational partition function and the rotational partition function. So let's review a little bit of what we did last Friday. What was the partition function, and how did we calculate it?
It was the denominator of the probability.
Okay, so let's start with that. The denominator of the probability. So in a probability calculation, it's a ratio. What's the denominator represent?
Number of events.
Total number of what?
Events or molecules.
Possible events, right? And in our case, we're talking about the probability of populating an energy level. So it's the total number of energy levels that are populated at a given temperature. And so then if you know the total number of energy levels at a given temperature, then you can pick a particular energy level and put that in the numerator, and you would see the probability of being in that particular level. And we had some examples of some two-level systems. You know, we did two-level systems, those calculations, because they're pretty easy to do. We did them with and without degeneracy. And I talked about two-level systems in the real world being like a enzyme antibody bound or unbound, you know, metal chelation, chelated or unchelated, or bond dissociation. It's hard, though, with the bond dissociation to get an equilibrium situation, right? Because it dissociates and it's apart. But I guess if you put it in a situation where the bonds are being formed and broken, like N2O4 versus NO2, you can set up an equilibrium there, and you can see the dissociated state and the combined state. And so there's simple two-level systems that are in actuality, you see them in nature. So a two-level system calculation is not just for fun. You can actually apply two-level system math to a lot of real-world examples. But today we're going to extend that thinking and go from a two-level system up to something on the order of 10 to the 30 levels. Okay. And so we're going to have to do some more math. We can't just make a table with 10 to the 30 rows. Right? We'd run out of time. We can't do that in 50 minutes. Okay. So what we'll do is we'll realize that if we're going to go to that many levels, distinguishing between individual quantum states is probably insignificant. We're not going to count those individual levels. We're going to integrate. So we're going to go from a discrete function where you can count individual levels to an integral where you just sum over all of the states and multiply by dn. So let's look at that. This is going to show you that there's really no sharp break where you go from the natural macroscopic world into the quantum realm. You know, it's just a smooth transition, and we'll see that today. So from the translational partition function and the rotational partition function, we'll see these smooth functions that are the partition function, and the partition function is a count of the energy levels that are occupied at a given temperature. So at low temperature, you might have one or two energy levels populated, and at a high temperature, it smoothly goes to 20, 50, all the way up to 10 to the 30. And there's no step, there's no discontinuity. And so that tells you that there should be a smooth transition into quantum effects. And we see that in spectroscopy as well. We see a broad smear of continual lines, and then as you cool things down, peaks start to show up, discrete transitions. So we've seen this before, but it's just another view of it by using the partition function. And so this is a bit of review. It's the denominator in the Boltzmann distribution. That's called the partition function. It's a count of all available states at a given temperature. We see in some textbooks beta being used, which is just 1 over KT, KT being the Boltzmann's constant times the temperature. My daughter's name is Katie, and so I always wanted to have a ball cap made for her that was beta to -1. People are like, what's that? She's like, that's my name. Your dad named you beta to -1? He's a P chemist, you know. So let's look at probabilities in a two-level system. And this is, I just show this part, not to revisit the two-level system really, but just to show that it's very smooth in going from the very cold temperature to a really high temperature. And I've got three things plotted on here, but two different categories of things that are plotted. Notice that the blue line is substantially different. It is not a probability. It is the partition function. So you see this blue here, the partition function. And then this is also, because it's on a similar scale, this is probability. So probabilities go from 0 to 1. And so the ground state probability is in red. So at really low temperature, the ground state has a probability of 1. Okay? And as you increase the temperature, molecules leave the ground state and go to the excited state. And this is the probability of the excited state, the green one. And so it starts to come up. At really high temperatures, we did this thought experiment last time and said, at super high temperatures, what's the probability? It's 50-50. So these approach 50-50. So 50% probability for both levels at really high temperatures. And then the Q is the partition function. It goes from 1 at really low temperatures, what is that one state? That's the ground state. And then it approaches, because it's a 2-level system, it approaches 2 at really high temperatures. So again, it's showing you that Q is a measure of the accessible energy levels at a given temperature. But what's interesting about this is this is kind of a strange energy scale. This is the temperature of the system divided by KT. So, or in terms of KT. So here the temperature of the system is equal to KT right here. And then the energy difference is 2 times that value, 2 KT. So when the temperature is sort of half the amount of temperature, the spacing and the energy levels, we already have some probability of being in an excited state. So here's the energy level spacing. So I'm going to just draw an arrow right here, 2 KT. So that's the energy level spacing. When we're less than that, we don't have enough temperature to really meet that, we still have some molecules being excited. And so there's some small probability that molecules, even though you, quote, don't have enough temperature to fully excite those molecules, in a large population, a few of them have that excited state. Most of them are in a ground state. Here's the probability of being in the ground state. It's not 1. It's a little bit less than 1. And so it's just showing you that in a system, you're going to have a distribution of molecules in this excited states and the ground state. And even though it doesn't look like you have enough energy for something to be excited, you do. It's like you're hot. This is not boiling, but yet it's evaporating. Some of the molecules have enough energy to get into the gaseous state. And so the probabilities reach the 50-50 mark at higher temperatures as expected. And then there's some small probability that the system will be in the excited state, even though the average thermal energy is less than that required for excitation. So let's look at a particle in the box energy. Okay. The particle in the one-dimensional box wasn't just a fun problem that we did last semester. It really is our model for translational motion. So in a molecule in this room, if I were to restrict it to one dimension, it could go to that wall or that wall, and that would be the length of the box. And so it's somewhere in between those two boundaries. And so the particle in a box is our model for translation. And I could just take that wave function in this dimension, and I could add to it or multiply a wave function in that dimension and multiply it by a wave function in this dimension. And then I get Lx, Ly, and Lz. And I have 3 different lengths. Okay. And so you can take that particle in a one-dimensional box and just move it to 3 dimensions by multiplying that problem. And that's what we'll see here. So this is our energy equation for translation. So we can calculate the partition function for translational motion using the particle in a one-dimensional box. And these energies are substituted into the definition of partition function. So this isn't anything new. This was on the previous slide. This is the definition of the partition function, and we're going to count the energy compared to KT. It's an exponential dependence upon that for every energy level, n being the quantum number. Okay. And so that energy equation related to N is right here. You should recognize this piece right there from last semester. Like, are you kidding me? You wants me to remember stuff from last semester? But doesn't that look familiar? E equals N squared, H squared over 8mL squared. So we just put that energy equation. We need an energy equation for our system. And in the past, it was just a two-level system. We just had ground state and whatever the energy spacing was. Now we have energy spacing that depends upon the quantum number. Okay. But realizing that at room temperature and with a box this big, think about L, it's in the denominator of the energy equation. With a box on the size of a room, you've got a really huge denominator, so the energy level spacing is really small. So there's very little difference between the quantum numbers. And so the n's are very closely spaced, and that's the variable we're counting over. So we can just integrate with respect to n, because there's very little difference between n's. Okay? So we can treat this energy equation as a continuous function in quantum number. And so we can do the integral. And I went ahead and got rid of the beta and put 1 over kt. So that's the equation. And so if we integrate that over all n, over the quantum number, then we end up with this result. I went ahead and pulled L out because we had this piece, this front piece, which is going to have the units of length. And so this is a shorthand for the one-dimensional translational partition function. It's the length of the one-dimensional box divided by this lambda, this capital lambda, which is our thing called the thermal wavelength. So this is a new term, the thermal wavelength. And it's, really wavelength, it's just in terms of length. It's just a unit, has a unit of length, okay? It looks kind of like the de Broglie wavelength or de Broglie wavelength. So that's why it got the name wavelength. So if you look at it, it has h squared on top, and you say, well, the de Broglie wavelength has h on top, but it's h squared, and it's got a square root here. So it's h on top divided by some small piece, which would have the units of momentum. So h over p is the Planck's constant divided by the momentum of the system, and that gives you the de Broglie wavelength. This is similar, so they call it the thermal wavelength because it's temperature dependent. And so this is something that's unitless, and so we can show how this partition function is unitless by looking at all the units here. We'll do that in the volume situation. So that's in one dimension. What if we do 3 dimensions? So particle in a box where kt is much, much greater than the energy spacing, and that's the case for all of these translational situations because we've got particles in enormous volumes. We can just make this, again, into 3 dimensions by multiplying that result. So essentially you cube the result. You have 3 dimensions, so it's the partition function times the other partition function times the other one. So the partition functions are multiplicative. So I will point that out here. Q total is equal to the product of all the other Q's. So this is yes?
You wouldn't have to go back to the integral to integrate over 2 different...
Well, you're going to get the same result that you got, only it would be a different L that comes out.
Are they all different?
It's the same mass of the particle. Yeah, Planck's constant hasn't changed. The only variable that's different in there is L. And you're integrating over the quantum numbers. And so L is the only thing that's different. Yeah, so you get the same factor in front, 3 times, so it's cubed now. It goes from 1/2 power to the 3/2 power.
Okay.
Yeah, and then then you end up with Lx, Ly, and Lz. So that's essentially the result of 3 of these one-dimensional partition functions multiplied by each other. And so I want to point this out for the video just to make sure that people get it down if you review it. And so that the total partition function is going to be the product of individual partition functions. And we'll see this many, many times. We'll see the translation partition function times the rotation times the vibration times the electronic. But here's the first example where we made a total partition function by multiplying the individual pieces together. So we took the x, the y, and the z and multiplied them. And also, I just always want to emphasize, y'all are probably very familiar with the capital sigma for sum, but the capital pi is product. And so it's just these individual partition functions times each other. So this thermal wavelength now becomes a volume. It's thermal wavelength cubed. And so we have the volume divided by the thermal wavelength cubed. Now it's nice to get away from volume because, if you have any slight changes to the system, volumes are a little more difficult to work with. We like to work with pressure because pressure is the same in all parts of the room. That's a nice and pretty well-founded assumption. Okay, so we can just convert volume to pressure using the ideal gas law. Now this can confuse you if you're not paying attention to the notes, but now we have another N that has a different definition. This N is number of moles. Okay, so right here we've made the substitution that the volume is equal to nRT over V. And so now this N is the number of moles. No really any way to get around that. N was our quantum number for translation. It has gone away because we integrated over it, but now another N is back, and this is now the number of moles. And so then you have all of these constants and so on unpacked, and temperature was down in the thermal wavelength. It was cubed because of the thermal wavelength cube, and then we have now temperature on top. And so we have the craziest unit ever, or in power, I would say, temperature to the 5 halves. So, you got to pay attention to the details. And the other thing, too, is the partition functions are unitless. And so this is going to be an added problem to your homework. I'd like you to show in your homework pages how this equation is unitless. In other words, what you're saying is, what units do I need to have for mass, for pressure? Really, pressure is an important one. The R, the gas constant, where all the units cancel, right? So if you were to calculate this problem, what units would you use? The partition function is unitless, and so you've got to get in there and see, do I use grams per mole or kilograms for my mass? Or do I use pascals for pressure or atmospheres, right? Or torr? So you've got to make sure that all those units cancel. Probably best to go with SI units, okay? So something on the order like pascals for pressure instead of atmospheres. Now you could come in with atmospheres, but you're going to convert them to pascals so that they're compatible with all the other constants. If you use constants with the wrong numbers because they have the wrong units, then you don't get the right answers because your units haven't canceled. If you don't use units, then you're not going to be able to do these problems. So I'll pause there. Anything that has caused you angst? Now's the time to straighten it out.
So this last part of the partition function is just in terms of pressure now instead of volume?
Yes.
That's the only difference?
That's the only thing that we changed, yeah.
So is R the gas constant?
Yes, R is the gas constant.
PV equals nRT?
Yes. And so then you would need to know which one. Is it? Well, it's going to be 8.314 joules per mole Kelvin. Okay, so that would be the one you would use. But then you're going to have to figure out how to get rid of the moles. And then the other thing that's nice about that is, let's say you got a per mole in there. You're going to have to get rid of that. And so even though you don't see Avogadro's number in there, if you have to use Avogadro's number to get rid of moles or to put moles in to cancel something else, you're free to do that. Yeah. So you multiply and cancel constants to work with the units till the units work out. So that's fair game. If you've got something, if you've got a mass in grams per mole and you want to convert that to just bare kilograms, you better divide by Avogadro's number to get rid of the per mole. Okay. And so then you're to grams, and then you've got to divide by 1,000 to get to kilograms. So you work the units till they all cancel out. And just really you're just showing, you're just doing a unit analysis on this. You've got Boltzmann's constant, it's going to be in joules per Kelvin. We've been using it in wave numbers per Kelvin, but wave numbers is probably not good here. You probably want joules per Kelvin because joules has mass in it. You've got a mass there. You've got joules cubed down here. So you've got all kinds of kilograms and meters and seconds. So, yes.
How do they test this?
Let's look at the next problem. We'll calculate it for argon, okay? And then we'll see if we can test it, okay? Yeah. And so what's the thermal wavelength and the translational partition function for argon at 1 atmosphere and 298 Kelvin? Now you can do this problem in your notebook and then check your work because it's shown in the notes. But this will be, let's just see, what is the scale, right? We've got the equation. Let's see what kind of numbers come out. What is Q for argon at 1 atmosphere? I picked argon because it's a monatomic gas. It doesn't have rotation. It doesn't have vibration. It's just a particle, and it's, it's abundant. It's almost 1% of our atmosphere. And then SATP. It's a new term for you. We'll define it later, but I'm using it now. So you've heard of STP, right? But what's this A?
Atmosphere.
Ambient. Yeah. Standard ambient temperature and pressure. So that means room temperature. They could have just said room temperature 1 atmosphere, but they could say SATP, and it's a little shorter. Okay, scientists are lazy. Or I say people are lazy, and scientists are people. Therefore. So that's. Now I didn't do this one in the select, in the sort of partial reveal. So just don't take it all in at once. Just work line by line. So we want to use mass. We want to get out of grams per mole, get into kilograms per mole. We look at the periodic table. We see that argon is 39.948. I said 39.95, but we want to use kilograms. And so I move the decimal place over 3, so it's 0.03995 kilograms per mole. I need to get rid of the per mole, so I divide by Avogadro's number. So that's the amount of kilograms for argon. And then here's the unit analysis for the thermal wavelength. I'm using Planck's constant here in kilograms meters per second because it's joules times seconds. This was joules times seconds on top. And so that second on top cancels one of the seconds in the joule. Okay. And then down here I have the mass in kilograms, so the kilograms cancel. Okay. I've got 2 kilograms down here, but I've taken the square root, right? So that works. So this kilogram is gone. That one. 1.38 times 10 to the negative 23. What is that? Yes, Boltzmann's constant. Okay, it's joules per Kelvin, and so this is a joule here. Kilogram meter squared per second squared. That's a joule per Kelvin. So here's the Kelvin to the -1. So that's Boltzmann's constant. And so then I have temperature in the bottom, so the temperatures are gone. I'm looking at this. I take the square root, so the seconds to the -2 cancels with the seconds to the -1 here. I end up with meters squared down here, but I'm taking the square root, so I have meters, and that just cancels one of these. So that gets rid of that. And I have a meter on top, and that's good. It's a wavelength. It should have a distance unit, and so I end up with meters. So that's the thermal wavelength for argon at 1 atmosphere room temperature. It's tiny, 10 to the minus 11 meters. Okay. Now, as far as a physical use for that number, it's really, I don't know of anything that's, that's ever been used. What is, that's a 0.1 angstrom, right? That's pretty small. It's certainly not the radius of the argon atom. It has nothing to do with the nucleus. It's just the thermal wavelength. Okay, I've never heard anybody do anything with that. You just take that and compare it to the size of the system that the argon is in. We can cube this. Let's say it's in a cube, and then put it in the volume that's taken up by 1 mole. So we've got, let's say we have 1 mole of argon, and put that in a volume of 1 mole. And so then that's what we have. We cube that thermal wavelength. We could have done the nRT over P. I just did it with volume on this one. And we end up with this partition function, 5.97 or 6 times 10 to the 30. So this is what I was saying. It gives you the idea of how many translational energy levels are populated at room temperature. So there, and it's going to be, plus or minus quite a bit. It's a smooth function. So there's a lot of energy levels populated in translational motion. In fact, it would be difficult to detect the quantum nature of translation because there's so many populated energy levels. How would you tell if that population changed a little bit? We're talking about, it went from 5 or 6 times 10 to the 30 to maybe 8 times 10 to the 30. I mean, it's still such a huge number. You really can't see that it changed at all. Let's look at this one. If that's the translational partition function at room temperature, let's say it's 5 times 10 to the 30. What is it at 100 C? So we've gone from, this is a totally different problem. So we're not talking about argon. So we say some molecule or atom has a translational partition function of 5 times 10 to the 30. What is that? What is that partition function at 100 C? And you may say, well, but I don't have the mass of the particle. I can't do the problem. And not say TE because this is my favorite kind of problem. Right? Because I like to give you situations where you don't have all the information that you think you need. But you have proportionalities. And so this is proportional to temperature to the 5/2 power. And so if you know the proportionality, you can make an equality by putting the 1s and 2s, right? You have the partition function that is proportional to temperature to the 5/2. And so you have this ratio of the partition functions would be the ratio of the temperatures to the 5/2 power. You don't need the mass, because if the mass hasn't changed, this ratio, the masses would cancel. Planck's constant would cancel. Pi and 2 and all of that would cancel. Okay, so all you're left with is the temperature dependence. And this is the craziest exponent, so you know that I would love that kind of problem. A lot of people will do these proportionalities, but they just think they're linearly proportional or directly proportional, right? They assume a power of 1, but that's a bad assumption. This is a 5/2 relationship. Okay. And so let's do that. We have the 5 times 10 to the 30 is the partition function at 298. And so then we have 100 C, which is 373 Kelvin over 298 to the 5/2 power. So it goes up to 8.8 times 10 to the 30. Pretty easy question to answer, but a difficult question to understand. You got to know the partition function and how it relates to temperature. Okay, but if you have that on your note card, right? So let's answer the question, how can we verify this, right? So let's see if translation, if we could ever detect the quantum effects of translation. We would have to either get into a really small box or really cold temperature, right, before the quantum effects would emerge. So let's think about what temperature would what temperature would display or reveal translation, say, as a 2-level system. So Q is at 5 times 10 to the 30, let's move Q all the way down to 2, where 2 levels are populated. At what temperature would that be? It's the same problem, but let's now change Q and see what temperature does.
Oh, so it's the same ratio. Then.
Yeah, it's the same ratio. So we just now flip this problem around. Let's go here. If the translational partition function is 5 times 10 to the 30 at room temperature, at what temperature would this become a two-level system? Would we start to see this quantum effect emerge? And so it's the same kind of problem. You have this proportionality, only now you want to change the partition function and figure out what happens to the temperature. So how do we get out of the temperature to the 5/2? Okay, so we need to, if you have the square root, you square both sides, right? Well, square root is to the 1/2 power. And so what you do is you raise it to the power of the inverse of that power.
Yeah.
So you put two ones, right, to the second power. So we just flip that fraction. So I can take this side and say, I'm going to take this and multiply it by the 2/5. Raise it to the 2/5 power. Right? And so then the 2's cancel and the 5's cancel, and I have temperatures to the 1. Okay? But I do the same thing to both sides. I mean, you can do anything you want to a mathematical equation as long as you do it to both sides. So it's just a little bit of algebra review. So then we end up with this equation over here. It's temperature 2 is equal to temperature 1 times that ratio to the 2/5. And so we can put in the temperatures. So we have 298 Kelvin, which is corresponding to Q1, 5 times 10 to the 30. And then Q2 is 2. We want a two-level system. We want to have 2 levels populated. And our temperature is 2.1 times 10 to the minus 10 Kelvin. We can't get there. So I don't think we would see the translational effects emerge. We've gotten to microkelvin. We've got to 10 to the minus 6 Kelvin. But if you think about how would you isolate and insulate a system so well that the outside world wouldn't influence it? We've got to get the heat out of it. And you've got to use expansion of gases and so on to do so. And so it's very difficult to get our systems down that cold. So I don't think we would see it. But we are starting to see in these, what they call Bose-Einstein condensates, we are starting to see is essentially the effects that could be explained by translational motion being quantized. Now let's think about what that world would be like. If we had an argon atom in this room and we cooled it down to something like 10 to the minus 10 Kelvin, and you set up, so now here's the box. What's the ground state wave function look like? It's a sine wave. It goes right here, and halfway in the middle of the room would be the most probable location for that argon atom. And so if I were right here, I would see the argon, if I could see it, more often than if I was here. But then in the second excited state, the first excited state, the second quantum level, I wouldn't see any excited argon atoms here, but I would see them over here because of the sine wave now has a node in the middle. And so we would be able to detect this quantum motion. But it would get confused if I had a third level. Now it's here and in the middle and over there. And so it's very difficult for me to see a single atom, for one thing, but it's also difficult for me to see a single atom and see that, okay, that one's the one that's in the third state, or that one's in the second state. As soon as I start getting more and more excited, fourth, fifth states, it starts to smear out again. So I could really have to cool it down to get it just in the ground state and the first excited state. And you can see that's very difficult to do. But that's what they're trying to do with these Bose-Einstein condensates. Now, what does that mean? The condensate part is they've got a gas that's confined in a vacuum, and so it's in a vacuum, so that's how they're isolating it from the rest of the world. And how they cool it down is they're confining it with lasers. So a molecule wants to move away, or an atom wants to move away, and it gets hit by a laser, and it slows it down. So the photon, it's just inertial confinement. It's confining it with the laser pulses. So they have laser beams coming at the 6, directions of a Cartesian system, and they're holding it in place. And so some molecules are able to escape that. Well, good. They're the hot ones. We don't want them. And so in any distribution, you've got some really cold atoms and you got some really hot ones. Well, guess what? We let the hot ones go away, and we're left with the really cold ones. And some of those might be at 10 to the minus 10 Kelvin. There's a probability that there's an atom there that's just not moving. So translationally, it's got a super cold temperature, and if we let the hot ones leave, then we're left with the cold ones. And we can start to see. If we send this, if we then pulse more lasers here, we can move this little gaseous cloud. And if we're able to send it through some slits, we might see diffraction on the other side. And so we would see diffraction of motion, which is a wave-like effect, which is a quantized behavior. So that's some of the things that they're doing in the physics experiments. So that's really all I needed to say about the partition function. Here's the plot of it from low temperature all the way up. You see it's a smooth function. At high temperatures, it's this equation. At low temperatures, you can go back down. Really extremely low temperatures, you could go back down to the summation and count the individual levels. So let's switch gears and do rotational motion and the rotational partition function. It's essentially the same treatment, but a different energy equation, right? We had the particle in a box energy equation for translation. Now we have the rotational energy equation. And so here's the rotational energy equation. B times J plus 1. Remember the carbon monoxide lab? That's the rotational energy equation that we're using. We're not using centrifugal distortion or any of that other stuff. We're just using the straight, what we call rigid rotor energy equation. We do have degeneracy, though, in this case. So here's the partition function. We had G. Let's see, G. So this is G here, and that's the degeneracy. At low temperatures, we can do the summation. At high temperatures, we do the integral. We're integrating over all of the quantum states. So dJ is our variable. And when we integrate over all of that, we get a super easy result. That's it, right there. KT over HCB. HCB is if B is in wave numbers, the HC converts it to joules, and so this is just, it's there just because of the unit conversions. If you take B in wave numbers and you divide by HC, you get B in terms of temperature. And so this is a shorthand right here called the rotational temperature. Theta B is called the rotational temperature. And so this would be B in wave numbers. C is in centimeters per second. And so you'll hear in this, it's called statistical thermodynamics, you'll hear a lot about rotational temperatures and vibrational temperatures instead of rotational constants. But it's just converting the rotational constant from wave numbers to Kelvin. Okay, so we're using Kelvin as an energy unit, which is strange. It's not energy, it's just temperature. That's the practice in statistical thermodynamics. So let's look at this. Diatomics are the smallest molecules. We have the smallest bond lengths and the smallest masses. And so I'm just showing you what are the ranges. We've done this in the first semester, just a review to show you if you're going to be dealing with rotational constants, you can simplify all those constants to 16 grams per mole per mu, which is the reduced mass of the molecule and the bond length. So the smallest molecule would be hydrogen, so it's going to have the highest rotational constant because the mass and the bond length are in the denominator. And so hydrogen is going to be the largest rotational constant. Everything else in nature is going to have a smaller rotational constant than that. That just means that the energy level spacing for hydrogen is as big as it's going to get. Benzene is going to be touching. Okay, but hydrogen is like the most quantized rotational motion would be hydrogen because the energy equation is B times J plus 1. B is the rotational constant. So the energy levels are farthest apart in hydrogen. And even hydrogen's quantized effects would be difficult to see at room temperature. So here's just showing you that its rotational temperature is 87 Kelvin. So once you're above 87 Kelvin, you're going to start to lose the quantized effect of rotation in hydrogen. Gaussian gives you these temperatures. So here's the Gaussian thermochemistry output. When you do a frequency calculation, there's a thermochemistry section. And in there, this is an asymmetric molecule. I did that so that you would get all three rotational constants, and here they are. They give you the rotational constants in gigahertz, but they also give you the rotational temperatures. And so this 30, that's the largest one. That's this hydrogen spinning around the molecule. So this hydrogen spinning around this way is the lightest mass, okay? And so that's going to be the largest rotational constant because the mass is in the denominator, so the rotational constant would be big for that hydrogen spinning around the molecule. And so that particular motion has this rotational temperature of 31 Kelvin. And then the other two rotations would be, rotating this way, like forward and back, and then rotating this way. So there are three rotations in every nonlinear molecule, and so those are the three different rotational temperatures. I just show you some math to convert the gigahertz to temperature. So let's look at the three-dimensional rotational partition function. Again, using our total being the product of the individual pieces, we have the three different rotational temperatures down here compared to the temperature of the system to the 1/2 power. And then we've got some extra constants out front that come from treating a three-dimensional system. This sigma is the symmetry number, and it prevents overcounting. So for a homonuclear diatomic, that sigma is 2. We don't want to overcount. Just like in probabilities, you don't want to base, like if you're rolling dice, there's 6 results, but what if you had only 3 numbers on there, right? If it was 1, 2, 3, and then 1, 2, 3 again. See, the symmetry of those numbers would cause you to think you have 6 events, but you really only have 3 events, okay? And so you don't want to overcount. And when you have symmetric molecules, that overcounting can change your numbers. And so they put in this symmetry number to keep you from overcounting. You don't have to derive all of this. I'm just kind of showing you what Gaussian does for us and how this molecular partition function was created. Okay. And so let's look at this plot here that shows the smooth transition from the counting to the individual energy levels counted down here to come up with the partition function, and it smoothly transitions into the integral form, which is up here. So for all normal temperatures, anything 30 Kelvin and above, we're going to have this integral result for a molecular partition function. And then if we're getting down to really cold temperatures, we might actually be able to count the individual levels. And in really cold temperatures, this just shows that the partition function goes to 1 and not to 0. Okay. So next time we'll talk about the vibrational partition function and the electronic partition function. And that's pretty much it. There's really 4 things that make up a molecule: translation, rotation, vibration, and then what's the electron cloud doing, right? So that can be excited and so on. The nuclear spin states, there's no energy difference, and so there's really no way to store energy in those spin flips unless you put it in a magnetic field. And so in that case, you would have a partition function related to a spin in a magnetic field, but we're just dealing with molecules in space, okay? No external field. So.